Flux of the magnetic field. I'm going to write this on top here. Flux of magnetic field through some surface area. The flux is always through some surface area. So flux of B field, put in parentheses, through some surface. And the surface that we will consider is going to be the surface enclosed by a loop of wire. And so we define flux as the area dotted with the vector B, which amounts to the same thing as A, B, cosine of the angle theta, where theta is the angle between vectors A and B. So let's draw a picture here for that. Let's say we have a loop here of wire, some wire. We don't need any current flowing through it. It's just a loop of wire. There's a loop of wire here. It's circular, and then the A vector points always in a direction that is perpendicular to this loop, and so it's going to point like this, 90 degrees. And what I have now is, well, I have that loop, and then let's say we have a magnetic field in this picture, so that the magnetic field points to the right. This points like that. And you have this magnetic field present everywhere here in this space, but I only drew one vector. So the angle theta is the angle between A and B. This is the angle theta. All right, and here's your equation for the flux of the magnetic field. It's easy to calculate this. So for example, might as well do a sample problem. So here's a sample problem. And let's say that I have, let's say that the picture looks like, well, let's just say I have whatever I have up there, such that the loop points, this is the loop, looks like this. Then I have the A vector and area. Let's say that the area is 2 meters squared. This is at 90 degrees to the surface. And then let's say that the magnetic field points conveniently to the right, like this. It has the magnitude of 3 Teslas. And then let's say that the angle between these here is 30 degrees. All right, so if I want to calculate the flux of the magnetic field through the surface, I would simply do the following. Flux is equal to A, B, cosine of the angle theta. A is 2, B is 3, and then this would be cosine of 30, and that's fairly easy to calculate. So let's do that. So we get 5.2. And then the units of this would be Teslas times meters squared. And we can keep it as that. Or we could rewrite this as flux is 5.2 Webers. So you could just put W for Weber. W. So Webers. So let me put here that Webers are Teslas times meters squared. Actually, it's WB, so this really should be WB for the symbol, and this should be WB for the symbol. So Weber's WB is. Well, anyway, so there's that. All right, so now we have this. We know how to calculate flux. Let's maybe do another one. So sample problem 2, and maybe what I'll do in this case is something like this. Let's say that I have this loop, and the loop still points like this. And A vector points in this direction. So here's the A vector, 90 degrees to the surface. And let's say that this is still 2 meters squared. But now let's say that the magnetic field points in the opposite direction, so that it points like this. Right, so here's the magnetic field B. It's still 3 Teslas, but now it points in the opposite direction as compared to the previous problem. So I need to calculate the flux here. So the flux is going to be A, B, cosine of the angle theta. A is 2 meters squared, B is 3 Teslas, then times the cosine of, well, I have to figure this out. So the angle that I'm looking at, if this angle here is in fact 30 degrees, if this angle is 30 degrees here, then the angle theta goes from here all the way to here, that angle theta has to be 180 minus 30, which gives me 150 degrees. And so I'm going to put here 150 degrees. And when I plug all of this in, I'm going to get that the magnetic flux is minus 5.2 Webers. And so something comes out of here, namely that if A and B more or less point in the same direction, kind of like in this case here, A points to the right and B points to the right, then the flux is positive. Then I get the flux being positive. But if A and B point in opposite directions, sort of like here, A points to the right, but B points to the left. So if the two vectors point in opposite directions, then you're going to end up with negative flux. And so, you know, if A and B point in kind of opposite directions, so I'm gonna write it this way. It's negative if I have these here. If these here are with quotation marks opposite, they're not really opposite. That is, they're not, you know, they're not pointing in totally opposite directions, but kind of. And if these here point more or less in the same direction, then you end up with a positive flux. And what I mean by same and opposite is here B points to the left, here A points to the right, sort of to the right. Here B points to the right, and here A also points to the right. So an example of a positive flux, here's an example of a positive flux. Let's say the loop looks like this. And then A vector just points straight up. And let's say that the magnetic field points like this. This would give you a positive flux. A and B more or less point in the same direction. An example of a negative flux would be where you have this loop that points like this, and here's A vector, and then you have, say, the magnetic field points somewhere here. So then A points in one direction, B points in the other direction, opposite directions, kind of opposite. You end up with negative flux. This would give you negative flux. This one here would give you positive flux. All right, so now we know how to calculate flux. It's easy to do. You should look at the, I'm on the bottom of this page here. You should do problems on the worksheet on the flux, and there are a bunch of problems there. Make sure you go through them and you know what you're doing. I'm going to add something to it. Okay, so let's look at this here conceptual problem, I suppose. It's not really a problem, it's just sort of an example. Let's say that you have a loop here, and the loop is the way it is. And then what we'll do is we're going to take this loop. Right now there's no flux through this loop because there's no magnetic field going through this loop. But let's take this loop and now put it in. So I still have zero flux, and then as I put this loop into the magnetic field, the flux is increasing because I gain magnetic field that points through the loop. I have more and more and more, and now I'm at the maximum possible flux. If I take this loop out of this magnetic field, then the flux through the loop decreases, and now I have zero flux. Flux is zero because there's no magnetic field going through the loop. I could also do something like this. Let's take this piece and put it somewhere out there. And now let's go ahead and slide this. So what I have is, I have flux. Now the flux is decreasing because the loop is exiting the magnetic field. Right, I only have half the flux I had before. Only half of the loop is in the magnetic field, and I take this loop all the way out, and now I have zero flux through. I have no flux through this loop at all because there's no magnetic field pointing through it. If I swing this thing back, I'm still at zero flux. The flux is still zero because there's no magnetic field pointing through this loop, and then I bring this loop into the magnetic field. Now I have some positive flux through the loop, and so there's flux is constant actually as I swing this thing through, assuming that the magnetic field is constant. This flux would be constant, and then it decreases, and then I'm at zero flux. All right, let's look at something similar but a little different. All right, so here we have this loop. Its A vector points to the right, and right now there's no magnetic field through this loop, and therefore there is no flux through it. Now let's bring this in. Now I have the magnetic field that points through this loop, and so I have flux through this loop. But what I'm going to do is I'm going to rotate this. And as I rotate this, note that there's less and less and less of the magnetic field going through the loop, less and less of the magnetic field going through the loop, until eventually when I'm like this, where A is perpendicular to B, at this point here, I have no magnetic field going through the loop. The magnetic field is just hitting the edge of the ring itself, but it's not penetrating into the inner surface. Right, and as I rotate this, now I have some field that goes through the loop. I have more field that goes through the loop, more field that goes through the loop. So this gives me positive flux, and then at this point here, the A vector is parallel to B, and so I have maximum possible flux. Now this is a maximum possible flux in the sense that it is a positive flux. When I go to this point, I have no magnetic field going through the loop, and so this would be 0. Flux is 0. When I go in this direction, though, the flux is increasing, but it becomes negative, right? A points in the opposite direction of B, so this is where the flux is negative. It's negative, it's negative. This is maximum possible flux, but it's negative. And if I go down here, the flux is still negative. It is still negative, but now it's decreasing, decreasing, decreasing. This might be actually a little confusing this way, so let's go back like that and leave it this way. All right, so what comes out of this one is, well, you should, one second, let me just set this up. Okay, so remember that the flux was A B times the cosine of the angle theta, where the angle theta is the angle between, it's the angle between A and B. And the vector A points here, the vector A. So if A and B are parallel, so if A and B are parallel, then you end up with angle theta being 0, and that gives you cosine of 0 being 1, and that's the maximum value you could get out of a cosine. If A is perpendicular to B, then you get theta being 90 degrees, and that will give you cosine of 90 as 0, and this is the minimum you can get out of a cosine. And so maximum flux is, in this case, this is a maximum flux, and this is a minimum flux. All right, let's look at one more case. So let's say that we have the magnetic field that points to the right, and it should do, here's the magnetic field that points to the right, and then let's say that we have a loop. Let's put a loop somewhere here. And I'm actually going to put this loop down here. So let's say that I have this loop, it's a circular loop, it looks like this, there it is. And I'm going to write, see if this might help. I'm going to write a circle. Circle, I'm going to put an arrow here that points like this. All right, now here's where I'm going with this. So I'm going to select this loop. And I'm going to move it right in here. So, well, actually, if I set it up like this, how much flux do I have through the loop? I have no flux through the loop because the magnetic field here is perpendicular to the A vector, right? A vector is coming at me, towards my face. So let me actually lower this and let me do, let me state that. Let me draw that. I'm going to get rid of that part. That I don't need that. So the A vector in red, you could either make it point into the page or out of the page. Let's just say it points out of the page. So this is A vector, points out of the page. So what you would have, A just points out of the page. And for this specific setup, this is what I would have. So if I bring this loop into the magnetic field, then what I'm going to have is A being perpendicular to B, and that's going to give me cosine of 90 being 0, and of course this will give me a flux of A, B, cosine of 90 being 0. There's no magnetic field going through this loop. The magnetic field sort of hits the edge here of the ring, but it doesn't penetrate into this area on the inside. All right, so now let's get rid of that because I'm going to need it. Let's select this loop and All right, let's bring it in. So now I put this circle in the magnetic field. There's no flux through this magnetic field because there's no magnetic field going through this loop. But I'm going to now rotate this in the following way. So picture this loop as sitting in a plane of the screen, but then it's going to come out of the screen. It's going to come out of the screen towards you like this. Right. What I've done now is I have made the I have allowed some of the magnetic field to point through the loop, and now the flux is no longer 0. At this point, when the loop is in the plane, in the same plane in which the magnetic field is, if the loop is in the plane of the screen, then there's no flux through this loop because a vector points straight out of the page, straight out of the screen towards me. But if I tilt that a vector, if I make this loop come out of the page towards us, then what I have here is now the magnetic field is pointing through this loop to the right, and there's going to be some flux going through it. Okay, I think this does for the concepts about the magnetic flux, the flux of the magnetic field through a loop. So you should solve some problems from the worksheet on the flux itself. You need to know how to calculate the flux. It's easy to calculate the flux, but you should practice it a couple of times.